Hello guys, this is me walking you through the cumulative review circuit. I'd have to say that this is probably the most important assignment to date because it's going to require you to bring back a whole bunch of skills, which is really good prior to the final coming up here in less than a month, or about a month. Happy New Year. It's probably New Year's. It's not yet, actually. I'm making this on Tuesday. But my intent with this is that it will be 15 test points, but it will be very easy to get all 15. You just have to do it on time, and I'm going to guide you through the circuit. You're just going to need to supply some work. All right, so I'll let you know. I'm not going to tell you which ones. I'm going to pick 15 of them, and I'm going to check that you have work. All right, so for this first one, number one, it's just a matter of factor, cancel, replug. Okay, so show the work for that, and that will lead you to number two. For number two, again, upon direct substitution, you're getting 0 over 0. You have two options with this one. You actually had two options up here too, because whenever we get that indeterminate form of 0 over 0, we could do L'Hopital's rule as well. So if you prefer that, on this one, you can either do L'Hopital's rule, or you can multiply the top and the bottom by the conjugate of the top. So you need to show work for either one. L'Hopital's rule, where you'll take the derivative of the top over the derivative of the bottom, which is 1, and then just replug that 0 in. Or you can do what we did in chapter 1 with this kind, the top and the bottom by the conjugate of the root factor, which happens to be on the top here. So that would be root x plus 36 plus 6. All right, and then again, factor, cancel, replug the 0 in. Regardless, it's going to lead you to the answer of 1/12. And again, I'm leaving the work off on the majority of these. Some of them I'm going to work all the way through. But so let's go find 1/12, which will be our number 3. And it looks like it's going to be on the last page, huh? 1/12. Where are you? 1/12. I must have missed it. I'll go more carefully. It's hard when I'm not doing this on paper. It's much easier on paper, isn't it? Hopefully you printed it off to do it. Looking for that 1/12. There it is. This will be your number 3. Upon direct substitution, this one takes you to, and again, when you're approaching 6 from the left, you still plug the 6 in. If we got 0 over 0, that indicates a hole in the graph. On this one, though, where I'll get a 12 over 0, and remember, whenever the denominator equals 0 and the numerator doesn't, that indicates that there's an asymptote at 6. Now, you could obviously cheat and go graph it, but again, being authentic is what's going to help you succeed and ultimately not have to take the course again. So we wanted to graph this one. You have to creep up on it, because when you have an asymptote, you can either only go up or go down. And to find that numerically, just pick a number to the left of 6, preferably really, really close, like 5.99. Square it, subtract 36. If your end game is negative, we'll go to negative infinity. If it's positive, we'll go to positive infinity. Again, you need to show the work for that. This one ended up being negative on the bottom and positive on the top when we approach 6 from the left-hand side, or like 5.999. So let's go find our negative infinity. And that will be our number 4. Looks like that's going to be on. I'm going to make bad choices with turning of the pages here, aren't I? Negative infinity right here will be our number 4. This is a piecewise function, and this is testing from chapter 1, our concept of continuity of a function. Remember, for a function to be continuous, the limit as you approach from the left has to equal the limit as you approach from the right, which has to actually equal the value of the function there to seal it all up and not have either this situation or this situation with a gap or a hole, which will disrupt continuity. So we're going to creep in from the left of 6, which would be this one, and we plug it in, right? Then we're going to creep in from the right of 6, which would be that one. You plug it in again, you supply the work, and then we have to see what happens at 6 which would be plugging a 6 into this one. If they are all equal, the function is continuous. And for that one, they were. So again, you're supplying work here as I guide you through. So that one is, if true, go to answer of -3. So let's go make sure that's not on this page so I don't miss it. And that'll be our number 5. Here we are, number 5. An instantaneous rate of change is a derivative. So you just need to take the derivative of this. Again, you'll supply the work. You'll plug in a -1, and you will get a 17, which will lead us to number 6. Come on, it's on the first page again, isn't it? Man, I am not getting lucky with the scrolls, am I? I'm looking, there's 17, and that's our number 6. Where's the function appear to be continuous but not differentiable? What that means is we don't lift our pencil, but we still have an issue with the derivative. And that would be at this cusp right here. But remember, when you have to explain a cusp, if it says justify, you'd say the limit as x approaches 4 from the left, not of the function, because they're both at 1, but it's of the, oops, sorry about that. It's of the derivative of the function. Let's say it was f, okay? It's not equaling. This slope over here is not approaching the slope over here. And so that's causing that sharp corner, sharp turn. It would not equal the limit as x approaches 4 from the right of f prime of x, okay? So that would be 4. Which will lead us to problem number 7. What is going on here? For some reason, there we go. Number 4 will lead us to problem number 7. Did I miss it again? Oh my gosh, you guys. It's going to make me crabby if I keep missing it. 4. I'm looking for a 4. 4. 4. 4. Sorry. I have to scroll like this. It's not like turning a page. And then I said that lead us to number 7. Here it is. This one's super easy. Supply the work to get me a -2. And that'll lead us to number 8. Let's make sure it's not on this page. A -2. And I think I'll do 2 videos here. In search of a -2, there's a +2. There it is, and that's our number 8. Okay, for this one, we're doing the derivative at e. Keep in mind, e is a constant in this scenario. It is like 2.7-ish. So when we do our y prime or dy dx, the derivative of e to the u is e to the u times du, or times u prime, and the derivative of x minus any constant is just 1. So that's that derivative, plus you'll supply the derivative of the natural log of x, plus the derivative of -1 over ex. And again, that'd be like -3x. Its derivative is the constant in front, which is -1/3. So this one would be minus 1 over e. Okay, when you're all done and you supply the work after plugging in an e, your answer should be 1. That'll lead us to number 9. All right, so we're looking for a 1 for number 9. Sorry if you hear that. One of my kids is laughing. A 1 for number 9. Must be on the first page again. My gosh, I am not getting, there it is. All right, number 9 down here on the bottom. All right, upon plugging in, again, with all limits as we approach constants, we plug them in. And tangent of pi over 4 is needing to be memorized because you know your unit circle, but sine and cosine at pi over 4 are equal. So sine over cosine at pi over 4 is 1. Over here, we'd have -1, 1, and -1 at those pi fourths for the tangent. So that does go to the 0. The bottom does go to 0. So we're going to use L'Hopital's rule. L'Hopital's rule says to do the derivative of the top, so you're going to supply the derivative of tangent x. The derivative of 1 is 0. The derivative of the bottom is also 1. You're going to show work for plugging in pi fourths. And ultimately, and again, your point is not going to be for the circuit. It's going to be for what I leave out. So I've been having some issues with key copying with not the majority of you, but enough to concern me. I don't quite know what that would gain you in the long run, but you're going to show work to give me a 2, and 2 would be our number 10. Another limit, but on this one's really tricky. I'm going to work this one out in full. I like the question though. Remember when we approach the infinities and we have these polynomial functions, it's all about where the biggest power is, because that takes over as we go to infinity. If it's on the top, then the function's unbound, or the y values will go either completely up or completely down. If the larger powers in the bottom, will approach 0. And if the powers are tied, then we steal the coefficients of the highest powers. This ultimately gives us horizontal asymptotes of the graph. So if ever, like this question could have said there's a horizontal asymptote at 2, instead of saying the limit as x approaches infinity. All right, so really when we analyze those highest powers, we could use L'Hopital's rule on this one, by the way, but that's not the best scenario when we have these tied function families, like they're both polynomials. So we might as well just do pre-calc where we steal those coefficients. So d is a constant in this scenario. So x to the first is what we're looking at on the bottom as the highest power. The highest power in the top isn't x squared, it's the square root of x squared, which is the absolute value of x. So we've got tied powers here, which means we steal the coefficients. We just have to be a little careful. So on the top, we'd actually have root a, absolute value of x. On the bottom, we'd have negative a x. Those are the ones in control, right? Now, we have to be careful with our signs here, and this one is tempting. It could make you go off circuit, because when we have a negative infinity, right, a is already negative. So when this goes to negative infinity, we'll have a positive on the bottom, right? On the top, as we, I'm really hungry. On the top, as we go to negative infinity, both of these will be positive. So we actually end up with positive over positive. So we actually will be having root a over negative a, or positive a. That's what has to equal 2. So now we have to go back and think of, well, how do we solve that? And the easiest thing to do is just think of exponents, and when you divide and you have the same base, you subtract exponents. So that'd be a to the 1/2 minus a to the first, which is a to the negative 1/2, right? Which is 1 over root a, because it'd be a to the negative 1/2 when you subtract the exponents, and that's what equals 2. I'm going to let you show the work for solving that. In the end game for this one, we would get, sorry, I have to find my sheet. I actually did all these. We'd get a being 1/4. Again, your points are going to come from all those things where I say you supply the work. So a equaling negative 1/4 will lead us to answer number 11. I'm going to do 16 of them in this video. So answer number 11 will be at 1/4. Let's hope I don't miss it this time, right? All right, number 11, equation of the tangent line. You should be really good at those. We've been practicing them all year. The only thing that's been changing is how we get that derivative. So we need a point. It says that x equals 8. So the y would be cubed root of 8, which is 2. We need the slope, which is the derivative. I'll let you supply that. All right. What's going to happen when you do your point slope form is you're going to have a fraction. So for example, if you had y minus 3 equals 1/5 times x minus 5, and if you want to put that into slope intercept form, this is point slope form, the easiest thing to do is to take this denominator and multiply both sides by it. So you would have 5y minus 15 equals, and then 5 times 1/5, they'll cancel, x minus 4, and then solve for y. That's what I'm going to suggest you do over here. You're going to get a fraction for your derivative. You're going to show taking it, that fraction is going to be a 1/12. So then when you write it in point slope form, you're going to have that fraction of 1/12. So multiply the left and the right by 1/12, like I did by 5 here. Then solve it for y, and then clean it up, the b. And your end b should be a 4/3. And that'll lead us to answer number 12, 4/3. Here we go. This one's super easy, so I'm not going to do any work. Remember, the derivative of a difference or sum is the sum of the derivatives. Doesn't work for products and quotients. That's why we have product and quotient rule. But that one's nice and easy. You just have to read your table. Your answer for that one should be 7 when you're all done. So answer 7 will lead us to, what number was that? Was that number 11 or number 12? Just a second. I don't want to be off with my numbers after going through. That was number 12, right? The 4/3 led us to number 12. So 7's going to lead us to number 13. So let's go find that. Number 7. 7, where are you? Here it is. That'll be number 13, right? I just want to make sure I've got, yep, that'll lead us to number 13. All right, this one's very easy as well, so I won't supply the work at all. But remember to do the product rule, first d second plus second d first. And don't forget there's a 3 in front of the whole thing, constant multiple rule. When you're all done, put in a 0, go read your table. And that should get you an answer of 24. And that'll lead us to problem number 14. 24 is going to lead me to problem 14. There it is. For some value, hello existence theorem, we have 3 of them. We have the IVT from chapter 1. If a function's continuous on a closed interval, then it has to pass through all y values on its way, like from -2 to 7. It's got to go through 3 at least once. All right. So this is on the interval from 0 to 2. And you're going to go look at your table. You're going to be looking at G. Okay, not G prime, just G. So no derivatives. This would kind of lead you to believe, well, this is probably the IVT. And it is. So you need to know the hypothesis of the IVT. If you're not 100% sure, you should go look it up. It's continuity, though, only. These come in for the NVT and Rolle's theorem. All right. So number 15 will be at -1/3. I have a terrible voice. I like to sing. I just can't sing. I can play the piano, I can play the cello, but I cannot sing. But Daddy, I just want to sing. That's from Monty Python. FYI. -1/3. Come on. -1/3. I can't find you. -1/2. Uh-oh. Oh, I thought I'd already done it. I was like, oh no. But that was my work for the sample to lead you to your answer for number 11. So this is number, is it 15 or 16? I think it's 15. But I'm going to make sure. Yes, it'll be 15 at the top of the page here. Second derivative. By the way, that notation, I want to show you why that notation is as it is, because you're taking the derivative with respect to x of dy dx. So you can see that there's that d squared y over dx squared. Well, you have to take the first derivative of this guy. You'll use the quotient rule. And then you're going to have another quotient. Again, you're going to supply all that work, which you can either write as a power, because you're going to have a constant on the top. Let's pretend it's 11, which it's not. And you're going to have something on the bottom. Let's pretend it's x minus 7 squared, which it's not. You have the choice of doing quotient rule again for your second derivative, low d high minus high d low, draw your line and square below. Or you could write this as 11 times x minus 7 to the -2, and then just do power rule, which is what I suggest. Either way, though, that answer should lead you to a 14 over a -125, and that'll be our number 16, which will be the end of this video. So let's go find number 16 at 14. I'm probably gonna make a bad choice again. Turning And I did. Oh, dang it. All right. Where are you, negative? Where are you? You guys, I swear to God, I really want to be doing this on paper, but I don't have that option. Why am I not finding it? 14, 125. I bet at home you're going, Thru, it's on the Lola page because you've got it on paper. 14. There. Good gosh. There it is. 16. All right. So we've got a function p. We're going to be reading off the table. We'd like to see those powers before we do the power rule. So we will do f of x to the 1/2 power. Be careful when you take its derivative because you're taking its derivative with respect to x being that independent variable, right? So you will bring that 1/2 out front. You will knock the degree down 1, but you always have to do the derivative of the guts. And the derivative of f of x with respect to x is f prime of x. So you're going to go to your table and you're going to do this at 1 and you're going to supply the work. And you should get a 1/16. And that'll lead you to problem 17. And that's the end of this first half of the video. So just to make sure you understand, if you just have what I have right now, you have 0 out of the 7 I'm going to correct out of those first 16. You have 0 points because you need to do all that stuff where I said, and you supply the work. All right. Awesome. I love you guys. Miss you guys. See you later. I will make another one for the second half of this shortly. Stop.